Let's take a look at an application for the empirical rule. So it gives us a sense of how powerful this is and then how we use it to get exact values in the next section. So this is an example, video example from our online homework, and it looks like we have some information about the mean weight of girls, one-year-old US girls. We know it's normally distributed. That's a key term, which means then we know the data, when we collect this data on one-year-olds, it's going to have this shape, meaning that the mean will be in the center, and then we'll have a standard deviation, in this case, of 9.5 kilograms, not grams, kilograms. And so that means the distribution would look something like this. You may have to pause so you can take a look at and draw this on your own here. And what that means, most of the people are going to be between 8.4 and 10.6 kilograms. Now I get those numbers again from the mean minus 1.1, the mean plus 1.1 as we look at that. And then we then can do another standard deviation below and another above, and then that's where we get those. And then we go 3 standard deviations above and below. So in general, we know 99.7% of all one-year-olds are going to weigh between 6.2 and 12.8 kilograms. And that's the power of the empirical rule and us being able to come up with some estimates, right, about, or being able to calculate the probability a one-year-old weighs this amount. And that's what we have here with these problems. Probability less than 8.4 kilograms. 8.4 is here. And then we're looking in this yellow shaded region. Everyone to the left would be someone who weighs less than 8.4 kilograms. And you get 16%. Again, this comes from kind of our distribution, how things are spread out in this picture here. Notice 8.4 is 1 standard deviation below. And so when we look at this here, we can see here's 1 standard deviation right here. We know that there's 50% is this group right here, from here to here, half of it, right? That's 50%. That's what you don't see, but it's cut in half. Then I know this is 68%. That means it's broken up in half, and that's your 34. So you have 50% plus 34 is 84%. And then what's left over is the 16%. And that's where that value comes from. It's the 100% minus the 50% minus the 34%. Again, because it's half of the 68. So there's a lot of ways to kind of try to calculate this. Now, later on, we'll use the computer ArtaStat to give us an exact value, but it's just a form of thinking, kind of the complement rule. How about between 7.3 and 11.7? That's 95% because that's 2 standard deviations. What percent is greater than 12.8? So how many what proportion of one-year-olds weighs more than 12.8 kilograms? I get 0.0015 or 0.15%. Now, how do you get that? It's again, that comes from the empirical rule, and this 100 minus 99.7 gives you 0.3. But those are the very extreme tails. I had mentioned that in the previous lesson. These very extreme tails. That's 0.3% of people. And you cut that in half because of the normal distribution. It's symmetric. So that 0.3, that left over here, you have 0.15 on each side. And that's where that 0.15 comes. In this case, 0.15% or 0.0015. And then as we think about this problem here, this class challenge, you could take a look, 7.5, 1.4 standard deviation. Now these are birth weights. 95% is going to be between these two numbers, 4.7 and 10.3. Now again, 95% because it's 2 standard deviations. So you're looking at a distribution just like this. And I love to draw the distribution which you have the mean and standard deviation. 7.5, 1.4, 1.4, and that's your 10.3. 1.4, 1.4 below, 4.7. And then we know 95% of the data is within 2 standard deviations. So that's again how we go about in getting these values. What is the relative frequency of more than 10.3? So we're looking at these little tails, less than 4.7. We're looking beyond, right? Beyond the 2 standard deviations over here. And remember, 5% cut in half is 2.5 in each, right? Because from here to here is 95%. Now we go ahead and put this back to this idea of z-scores and connecting back to something like this, where if the mean of the class scores on the test was 72 and with a standard deviation of 4, find the scores of a person who had a z-score of 2. So this requires a little bit of hand calculation, right? So if we know the mean and standard deviation and their z-score is 2, that means, right, they're 2 standard deviations above the average. So that's why we're doing 72 plus 2 times 4, the standard deviation. Again, it comes from the formula for z-score right here, because we're trying to solve for the x value. When we know the z-score, we know the standard deviation and mean, we end up using that little calculation there. What if they score 1 below? Well, it's 72 minus 4. So some of you may not even need the formula to do it. You can kind of think it through. But there's your z-score to find an x value with your mean plus your z-score times the standard deviation. Now, your z-score is positive or negative, it brings you above or below. And so if someone has a z-score negative 1.5, what is their actual score? That's what you would get.